Start the recording after the roll in attendance so that if you're attending and have to come back to the overall class stuff, that you're not having to sit through the attendance stuff, because we got to keep track of attendance, and I hate taking attendance. You guys are all adults, and it's your responsibility, and my verification that you have attended class is the weekly evaluation form that I want you to fill out. That's what I'm doing to count whether or not you're actually in class. This I'm doing for social or tracing if something were to happen. And please use discretion over the weekend. You know, there's some entertaining things happening in the state of Oklahoma this weekend that one I would count as a super spreader event is occurring. So just use discretion. All right, and I'll tell you the story. I actually had dinner at the end of February with a colleague of mine. We spent the whole weekend together in a meeting. I found out 7 days later that she was positive for COVID because it was the last weekend in February that we actually were out and about and did things. Found out 7 days later she was positive for COVID. And we found out that where she got positive was the Boston Medical Conference that had occurred. That was one of the first super spreader events in the United States. And she rode in a car from the airport. She picked up a friend from the airport from that event, and that's how she contracted COVID. And so she was one of the first people that I knew that actually contracted it. And it was from a super spreader event. So that's why I worry about those. All right, so now, I have to remember if I'm in an ITV classroom or if I'm in my other classroom, how we get to spread things around is going to be entertaining. Okay. Got to hit the right buttons. Okay, can everybody hear me?
Yes.
All right, good. All right, so this is Blackboard. So that you can look in Blackboard. I've had a couple of things, and one reminder that I didn't in all of the other extra announcements. And some of you have emailed me, and my first question back is, which class are you in? I teach General Physics 1, Engineering Physics 2, Concepts of Physics, Concepts of Chemistry, and Introduction to Engineering. Later in the semester, I'm likely to know exactly which class you're in. Okay? Later in the semester, I'm likely to know exactly which class you're in. But this week, ain't happening. Ain't happening. So when you say, I have a problem with week 1 on Blackboard, okay, that's 5 week 1s. I got to figure out which problem you got. So help me help you. Because if you say, I'm in my general physics class, that makes my work a whole heck of a lot easier, and I can help track down your problem, or your issue, or your concern. The other thing is, I don't like to feel stupid. So if I'm in my office and somebody says, I got a problem, and I say, well, if you're on campus, come down to my office. Well, 3 days a week I'm in Tonkawa, 2 days a week I'm over here in Enid, and it would help me, particularly for you guys' class, to let me know if you're on the Enid campus or you're on the Tonkawa campus. Because then I don't say, just come see me in my office, and I'm on my wrong campus. So that does help me a little bit. And it also tells me where I might be able to point you to some resources over here versus resources over in Tonkawa. So just help me help you a little bit on that, and we'll get through that part. So that's one of the things that's out there. I have tried to post the Zoom link in a variety of spots. I've done the one here, there. I've got the class key for the Pivot Interactives, and I did get a couple of questions about the McGraw-Hill stuff. Your book and your online homework are in WebAssign. McGraw-Hill we're going to use for some virtual labs, but because it's a beta test, it's not working just right yet. So I know if you click the McGraw-Hill thing, it's going into Never Never Land, and I figured this week I wasn't going to mess with that. I'll figure that stuff out next week so we don't add to the confusion. So just be aware that the McGraw-Hill is going to be for laboratory interactives and some of the virtual labs, and it's a beta test, and we're working on that stuff right now. So you don't have to worry about it until I tell you to worry about it. Okay? I have not checked to see, I have opened the Pivot Interactives. The next week will be the first time that I'm going to actually assign something out over there. So over the weekend, if you want to get in and familiarize yourself, go ahead, great. I mean, really just do that, but I don't have anything that's due for the Pivot Interactives this week. I had a question about extra credit this week. Well, first of all, you've only got the getting acquainted with WebAssign part. And please, when you look at it, read in the getting assigned, or I had about 4 different folks email me saying it wasn't taking the backslash. It's because it wasn't a backslash. It was a lowercase l, which is why it wasn't taking it. Okay? And that's why I talk about formatting problems in WebAssign, is that sometimes how you put in something in scientific notation is going to be a little bit different than what you've got on a few other aspects. So that's one of the things that you got to kind of look at and worry about. And try a couple of times to see if you get the formatting right, then email me and say, check and see if it's a formatting problem. And I'll try and check it. Now, pre-works are generally 5 to 10 points. So I don't worry so much about this week getting the extra credit, because it's 10% extra credit and you're talking about 1 point. When you're on your homework ones, which are 50 points, that's a big deal, because that's a lot of extra credit points. So this week, I wouldn't sweat it too much that the 48 hours it was a little tougher to get, but you've got that going forward out there. Questions? Now that we've been through the class a couple of days, you've had a couple of days to think about it. Anybody got any questions on that stuff yet? And I hope those of you who've emailed me know that I try to respond fairly quickly. However, responding after 9 o'clock at night ain't going to happen. I'm an early bird, because I know some of you noticed that they got an email before 6 a.m.
Early bird gets the worm.
So you're likely, and it is not uncommon for me to wake up in the middle of the night because I am an insomniac. And it's not uncommon for me to send you an email back at 2 or 3 in the morning. But do not expect that all the time, and do not expect me to want to respond to an email after 9 o'clock at night. Actually, after 7 o'clock at night, it's highly unlikely that I'm going to respond. And it's highly unlikely that I respond after 3 p.m. on a Friday until sometime in the weekend. Okay? Because by 3 p.m. on Friday, I'm toast. I am toasted. I don't do so good after that. So, which is one of the rationales why I do the 48 hours in advance is physics is like a puzzle, right? So that for all you puzzle people, a physics problem is a puzzle. And the physics problem is figuring out the trick to the puzzle. Okay? So physics is a puzzle, and you're trying to figure out the trick to the puzzle. So, and I know all of you have done this, you've been working on a puzzle, you work on a crossword puzzle, you start the problem, you start it, you work on it, and you get stuck, and you leave it for a while, and then you come back and it's like, well, why did I have trouble with this? Because psychologically in the back of your head, you're still working on the puzzle. And for all of you that start your homework at midnight on the day before it's due, you don't have the opportunity to have what I call dwell time, or have your brain work on the puzzle. And I cannot tell you how many times that I would work on homework, and I would start it, and I would be so freaking stuck, and then I'd go to bed and have a good night's sleep, and the next morning I'd just go out and just solve the problem like there wasn't ever anything difficult about it. So by doing it 48 hours in advance, even if I haven't presented the material, 2 things happen. One, you're going to listen because you've already tried to work on the puzzle. And when I say something, you're going, that's the trick that I needed, or that's the little solution part that I needed to help me solve the puzzle. So by looking at it ahead of time, that gets you there. It also gives you an opportunity to say, okay, I've tried this for 2 days and I can't figure this out. And you're able to ask a good question. Okay? So that's one of the reasons why I do the 48 hours in advance. Is because, if you do it ahead of time, if you wait till the last minute, you're toast. You're likely to run out of time. And that's one of the issues that you've got. So that's those are the kinds of things that I utilize it. And I will tell you, my son has been where you all are. My son is 1 year away from graduating with his PhD in experimental psychology. So he thinks like you guys do. But I also have because he's done psychology and he's working on psychology, I get an awful lot of why the brain works that way, which is kind of interesting. And actually, if you read his research work, it's all chemistry. And I did laugh because I actually read his master's degree dissertation, or whatever they call it over there these days. And I know there was a whole sentence that was just in RNA, DNA gobbledygook. Because he actually looks at the changes of the brain when we learn. That's what he studies. He studies how so it's kind of interesting that we get there. So that's one of the things that we've got. So I'll talk about another thing that we do. I didn't bring my prop, I'm sorry. I didn't bring my prop. Because what will happen is when we're working with physics problems, how many people deal with Legos?
If you mean them as a minefield, then yes.
No, I'm talking if you're just playing with Legos. You've all played with Legos. You've all put something together with Legos. Do I have anybody who has never played with a Lego? And I'm even talking about duplex. It doesn't have to be the Lego brand.
It can be the bootleg knockoffs.
It can be the bootleg knockoffs. It can be anything, brick blocks. Okay. So what happens is in physics. First of all, we all know where physics is in the science spectrum, right?
It's in the middle between science and math, pretty much.
Well, actually, mathematics is the language of physics. Okay? Mathematics is the language of physics. Because math, all your higher math was actually derived and dealt with generally by physicists to get there. So mathematics is the language by physicists. They call chemistry the central science. Physics is the rules. Okay? Physics is whether or not you've got an 8 Lego brick or a 4 Lego brick or a 2 Lego brick. Okay? It's the rules that we're going to put together. So that's where physics is in all of this. Physics is, I'm going to go ahead and turn the camera on instead of the blackboard at the moment, see if we can get this. Maybe. See what happens. Try that. Okay, so you guys can see me. Alright, so physics is actually the rule. And in fact, physics wasn't considered to be a science until about the early 1900s. If you went to go find a physics book, you would not find it in the science, in the Dewey Decimal System science categorization. You would not find physics with all the other science books. It was over under natural philosophy or synthetic philosophy. Okay, so it wasn't really where we talk about what we traditionally think of science. Physics wasn't there. It was more of trying to figure out how things work. And in fact, if you actually go back and look at some of the big names in physics, like Newton, Hooke, a lot of those folks, they were elders in the church, their particular church. Okay? So they were coming at it from a very different thought process, and they did a lot of thought experiments. They would take logic and move logic through, which is hence why it was called synthetic philosophy. And they would look at logic. So physics comes in and they're trying to explain what they saw and what they observed in the world. So we end up with dealing with observations. And I will tell you, because when you tell somebody you're taking physics, what's the first thing they look at you and say? So when you went home and told your mother you had to take physics, what did they look at you and say?
Good luck.
Good luck. That was good.
That was literally what they told me. Good luck.
Good
You're
luck.
gonna need it.
Good luck. What are some of the other ones? Glad it's you and not me.
The other thing they said is, I sucked at it, but if you're good at math, you'll be able to do it.
I was so good luck, you're on your own.
Yeah, good luck, you're on your own. I love it.
Same happened to me.
Good luck, you're on your own. Okay, well, I will give an example. First of all, you're going to be able to do more physics in your head than we ever will be able to do on a piece of paper. All right? I love to give the example of my daughter, and it turns out I have a friend of my daughter's in my concepts of physics class, and I used her as an example last night. They're both equestrians. So let's think about physics. When you think about physics, we think about balls, tossing balls into the air. We think about rolling balls down the hill. We think about projectile motion. Then we get really complicated and we say we're going to deal with electricity and magnetism, and then we deal with optics, and then you get the weird stuff if you watch Big Bang Theory, because they're all doing particle physics and they're all doing string theory and other weirdness out there, which is not me. I don't do that weirdness. That's weirdness. But I will tell you that all of the equations that you see on Big Bang Theory are actually correct. They do have a physicist that goes out there and makes sure that those equations and those things are correct on the chalkboard. So those are correct. But the thing is that we deal with it, but these two equestrians not only do the physics for themselves and in their body mechanics to be able to position it, they also do the physics for the horse that they're riding. They actually, before they come into a jump, they know when they have to give the horse the cue to lift off so that it's going to clear the jump so it will land properly on the other side of the jump so it can make the next challenge. So not only are they doing the little bit of physics that we would do if we were trying to aim, play the old monkey in the gun game where you got the monkey that's falling and you're shooting towards the monkey and making that calculation in your head, the equestrians are doing it for them and their horse. So you think about that, and you think about, okay, now how am I going to put all that mathematics together to actually explain it? Well, we're going to start to do that. That's one of the things that we're going to start to do. So in Blackboard, I think you all saw, I hope I put it there, I put out a new video. It's called Estimations and Rules of Thumb. Because one of the first things that we do in this first chapter, and I will hear it, somebody over the weekend is going to email me and it's going to say, we haven't learned this yet. Well, that's not the point of the homework in this chapter. The point of the homework in this chapter is to show you, one, to do estimations, okay? To use estimations and rules of thumb. The other is to get you to use unit analysis to help you solve the problem. So even if you don't know what the underlying physics of that particular thing is, all you're doing is putting the units in. And I'll show you the unit analysis here in just a second. So that's what the point of all of this is. So let's take some rules of thumb. So I've got the video out there. You can go look at it at your leisure. And I do a couple of estimations. One estimation that I do is looking at the number of heartbeats, an average number of heartbeats in a single day. I also look at the comparison of teaspoons of atoms in a teaspoon versus teaspoons in the Atlantic Ocean. So I encourage you guys to go watch that video because it's really going to be helpful. But the key is we want to deal with certain things that we're going to deal with in the language of physics, and one of those things is we've got to get our hands around rules of thumb. All right, so we're going to do this, and hopefully things will work. So let's start with this. We're going to start with this. So I'm going to write some things down. Okay, it didn't go. All right, try it again. Make sure you get all the buttons pushed. Okay, we're getting successful here. Maybe. There we go. All right. Everybody can see that? So my first question is, what are those?
Numbers.
I got somebody that just told me their numbers. All right. Cool, that's all they are. They're numbers. Actually, one of them is a very special number. It's a little hard to see. Also, for you guys, I use a Latin 7. That's what that's called. The 7 with the dash in it is a Latin 7. And the reason I use it is because people out there will do a 7 that looks like this, or a 2 that looks like that, or a 7 that looks like, or 2 that looks like that. I need a little more clarification than that. So I use the Latin 7. So that's, if you're not familiar with it, that's what it is. It's called the Latin 7. Okay. So we know they're all numbers. I am persnickety. I'm persnickety about a lot of things. I'm persnickety in physics class and in chemistry class that they're just a number unless it has units. So I put these up here for a variety of reasons, but one of these is allowed to not have units, and that's 3.14. It's pi, it's a ratio. And if I'm working and doing a problem and I put 3.14 in there, it's a number. And so I don't necessarily need to have units associated with it. But most of the time we're going to deal with units. So several of these numbers that I put on there, you also immediately put a connotation to. Look at number 7. What did you think of when you see the number 7? And we're in physics class.
Days in a week.
Days in the week. So 7 could be days. And we have a conversion factor of 7 days a week. So I'm going to ask the question, and I want honest answers. Because how many people in here have taken general chemistry?
I'm taking it right now.
Okay, we got people taking general chemistry. You know, general chemistry is all about just conversions, fundamentally, just conversion. So I'm not going to spend a whole lot of time on conversions. I gave you a conversions video to sort of remind you about conversions, but we use a lot of conversion factors. Okay, we use a lot of conversion factors. So 7 days in a week. So what's connotation when I put up 365?
365 days in a year.
Days in a year, right? 39. Oh, come on. In physics class, unless stated otherwise, we're going to use the SI system of measurement. System International, which means we're going to use kilograms, meters, seconds, all that lovely thing. So what would 39 be? How about inches to a meter? Pretty close. It's a little off, but pretty close. The actual one that you should remember and build into your head, 2.54 is an exact. So it has an infinite number of significant figures, and that's centimeters to an inch. Okay, that's centimeters to an inch. And a meter is roughly 39 inches. Roughly. Now, I don't expect you to know what 27 is. But 27 is one of those that I want you to start getting in there for a rule of thumb. Because what we're going to start with, it looks like we're going to start with it on Wednesday. What we're going to start with on Wednesday is start dealing with one-dimensional motion. We're going to start with kinematics. And we're going to look at what the displacement versus position versus motion. We're going to look at velocity versus speed. We're going to look at acceleration. We're going to look at all of those things. And we're going to do it in the metric system. Okay, we're going to do it in the metric system. And when we do stuff in the metric system, because that's not how we live with the common system or the English system. When you do a calculation, to give yourself a rule of thumb to figure out, am I right? Does this make sense? We got to kind of look at that. So if I tell you 27 meters per second, which is one of the reasons why I do that one, this is a rule of thumb thing. 2.54 centimeters is an inch. And by the way, most of you have an inch reference on your person right now. On most adult human beings, from here to here, on your index finger, is pretty darn close to an inch. Mine actually happens to be exactly an inch. It's one of those weird facts of life. You know, some people some people have longer ones, but you know, for most human beings, that's pretty darn close to an inch, which is where the yard came from the tip of the nose to the end of the fingers, where a lot of our imperial, and that's where we got the imperial units, is because you were dealing with whatever the king was. Or during the time of Elizabeth, whatever her dimensions were. But that's where you get the imperial units. So 2.54 gives us an inch, 27 meters per second. When you do the conversion, so this is a good conversion to practice. When you do the conversion of 27 meters per second, you're going to get 60 miles an hour. So it's a good one to say, if I'm driving down the car down the road, and you all of a sudden get 365 meters per second, you're going to go, I don't think that's a car down the road unless it's the Darwinian one where the guy's on the jet car. You know, that's just not a typical number that we're going to have in that particular problem. So we can use our rules of thumb to kind of give us, are we in the right ballpark? It's also a good way to evaluate whether or not the newspaper is giving you an accurate number. If somebody tells you that the quarterback threw a pass for 230 yards during the game, we're going to go, that's a misprint, dude. Why?
It's 100 yards on a football field.
There's only 100 yards. It's actually 120 on the outside of the end zones. Yeah.
So that'd be about 250.
That'd be 2 football fields, and you only, so you know that number's not quite right. That number doesn't make sense. Okay? So that's one of those things that you can look at and I will admit, I try very, very hard for any example that I provide. Unless I tell you otherwise, because I'm making it up on the fly. Okay? Unless I tell you otherwise that I'm making it up on the fly, that I have tried to give you a problem that's going to give you a realistic, reasonable, physical answer. There are times that I'm going to plug in numbers just because it's easy for me to do as an example because somebody's asked a question in class. And the numbers are going to kind of go, they're going to look a little odd, and I don't necessarily have that good feeling for them. But I'll give you a caveat that I'm just pulling numbers out of the air, so I don't know if those are realistic or not. But when I give you the weight of a diesel engine, when we do a collision with the diesel engine and a Volkswagen Beetle, I will give you numbers that are reasonable, that are going to make physical sense. Because that's what we have to do in physics, is we're trying to make physical sense of what's going on. So numbers have units. Unit analysis is really going to help me out. Okay? So we've all done the algebra problem, right? We've all done the algebra problem. Fred moves with a speed of, and I'm going to go ahead and do it as 45 miles per hour, travels for 3 hours. What distance did he travel?
$135 miles.
135 miles. Now, this, because I see this all the time, and this is what you guys probably had happen to you all the time, is do I multiply or divide to get, if I want the number of atoms in a mole, do I multiply or divide to get me what I want?
You're overthinking it.
Well, not only are you overthinking it, but if I write this out, this is where unit analysis helps me out. If I do an hour, right, and I do 3 hours, which is exactly what you all did, yeah, I can cancel out my hours, and I know I've got my miles in the right place. Now, what's going to happen to us a little later, and we're going to see this probably on Wednesday, I'm going to say that acceleration is equal to position times time. So I've got position, we'll do velocity times time, sorry. It's going to be velocity times time. Velocity is going to be in meters per second. Time is in seconds. Oops, that's not right. Because acceleration is going to be in meters per second squared. If I do it like this, that can't be right. My unit analysis says it can't be right. This needed to be velocity divided by time. Because that's going to give me meters per second divided by seconds. This means meters per second squared. So it's going to help you tell whether or not you set up your equations correctly. Okay? So unit analysis is really going to help you deal with those equations and show you, did you set up your equation correctly? Or did you manipulate your equation correctly? Did I divide where I should have multiplied, or did I multiply where I should have divided? So that's where, so what you're getting in the one problem that you've got for homework, or should show up for homework, is I don't care what the equation that they gave you. What they're trying to say is whatever's on this side of the equation is equal to that side of the equation in terms of units. So I'm going to make up something. So this is going to be x, and we got t, and we're going to divide it by b. Okay, x is going to be, we're going to use it as position, which means it's going to have units of meters. Velocity is going to have units of meters per second. Time is going to have units of seconds. And we're going to ask if that is the same as, we're going to do acceleration. We're going to ask if that's the same as that. And m is going to be mass. And it's going to have units of kilograms. Well, if I don't have mass over here, and I got mass over here, we know that immediately is not equal. Okay, we know already that those two things aren't equal. And one of the things in physics is I have to add apples to apples, and I have to add oranges to oranges. So if I'm in meters per second, I can't add meters per second squares to meters per second. I can't do that. So my unit analysis is really, really going to help me make sure I've done the manipulation correctly, make sure I've set up my equations correctly, and make sure that I'm working within there. So when you get to that problem, we know at the first chapter that you've probably never seen it before unless you got lucky and took high school physics. And we live in the lovely state of Oklahoma. And we're in Enid and we're in Hopawalk. So unless you were like in Edmond or maybe Ponca or Enid High School, not necessarily so much if you went to Fairfax. The opportunity to have had physics in high school in the state of Oklahoma is not all that great. So we don't expect you to know that. That's not what that problem is actually designed for. That problem is actually designed to have you start playing with the unit analysis. The other idea of why we tell you to deal with estimates is we call that a back of the envelope check. Okay? If we do an estimate, we want to know, is that back of the envelope check make physical sense? And it gives you a way to look at it. We don't have to do it so I'm going to date myself, right? Totally date myself. My first computer, I had to build myself, not counting a traditional calculator. My first computer I had to build myself had 65K of memory.
That's not much memory, is it?
Did a heck of a lot. We put people on the moon with that. My first research computer used paper tape to help program it. Okay? Your smartphone now has more memory than probably my first personal PC that I had. Okay? So if we think about that, and we think about even my calculator. My first calculator cost me $360 in 1979. So, when we were doing this stuff, we were using a lot of mathematical tricks to figure out how to solve these problems and do these calculations. So that's why you would do a back of the envelope calculation, because you needed to figure out, am I in the right ballpark, have I done the right thing? That's why we use scientific notation, because scientific notation was a heck of a lot easier than trying to deal with a big huge freaking number. That's why we use logarithm scales. That's why we use all those, because we use slide rules. I was the last class that had to actually learn how to use a slide rule when I was a freshman in college. Last class. I was also the last class that actually had to punch Fortran cards to use the mainframe, because we were the first ones that we could actually do direct programming on the mainframe. So that's why we do a lot of this. That's also why we force you to go through college algebra, or algebra for STEM. Because you're sitting there going, okay, what are you really doing? You're solving the quadratic equation 20 different ways. And you're all looking at yourself going, I can punch it into the calculator. Why do I have to do it this way? Because we only had 65K worth of memory to try and do it. And in order to get it into that 65K worth of memory, we had to simplify the problem. And if any of you watched, what is it, the Rocket Girls, or the whatever they currently have the movie up, the human calculator, Chuck Yeager wasn't going to go up unless she verified the calculations of the computer. They didn't trust it. And so you really did have to do the mathematical tricks in order to solve the problems. Hidden Figures is what the book's The Rocket Girls, but the movie's Hidden Figures. So I mean, that's why we do these things, and that's why we force you guys to get there. And we are actually going to use some of those mathematical tricks to solve the problems. So if you want to review some mathematics, 2 equations, 2 unknowns. And one of the things that I will do in Blackboard is I will use the OpenStax College Algebra Trigonometry book, and I think I've already done it for this first chapter, is that I will point you to the section where that math review is. All right, so that you guys can go back and look at it if it's been a while since you've done it. So 2 equations, 2 unknowns is one of the big ones that we use, and we're going to use that one a lot. And we're going to use the right triangle for trigonometry. So let's go ahead and look at the right triangle. Get that one out there. So I'm going to draw my right triangle. I'm going to use that one. I'm actually going to do it in different colors. We got it in different colors. And then we've got our angle here. Okay? We got it in different colors. And we all, now your book's going to do it this way, right? They're going to say that this is R, they're going to say that this is X, and they're going to say that that's Y. And the reason we do that is the Cartesian coordinate system, right? Because if I do this in the Cartesian coordinate system, this is on the x-axis, this is on the y-axis, and it's all well and good. And the reason we do that is because we actually work with two different coordinate systems. We've got our Cartesian coordinate system where this is x and y, and we have what we call the radial or polar coordinate system where this would be done as r theta, whereas this one is done as x, y. And we can convert back and forth between the two. So that's the right triangle that we're going to use. We're going to convert between the two coordinate systems because we're going to use the two coordinate systems for a variety of different reasons. And we can throw in the z, but we're going to be nice, and we're only going to work in 2 dimensions. We're not going to mess with 3 dimensions. That's why you're in college physics and not engineering physics, because we get mean, cruel, and wicked in engineering physics. We do the 2 dimensions, or 3 dimensions. We throw in the third one. So we got that, okay? Now I'm going to tell you, this is going to get yourself confused. Looks good now, but I'm going to tell you it's going to get yourself confused because physicists are strange people. And yes, I am a physicist. So I got it. So just to let you guys know, I have a PhD in physics, but it's actually chemical physics. I play in both chemistry and physics, which is why I don't do the particle thing. That's not what I do. Actually a light scatterer by training. I worked in environmental science for a long time. I understand why an NMR works like an NMR does, or an MRI works like the MRI does. Gas chromatographs, infrared instrumentation, I'm a light scatterer, because that's how we do a lot of analytical chemistry. So that's my background, that's what I do. But this right here, physicists are strange things, and we're going to deal with something called an inclined plane. Okay, so an inclined plane is we've got a plane here, and we're going to put our little car or our box or something along that plane. And all of a sudden, my car and my box on my plane, if I'm trying to deal in a Cartesian coordinate system, is a pain in the tushy. Because I really want to do it this way. Where I'm going to make that horizontal, and I'm going to be able to draw my triangle. So what I want to be able to do is I want to be able to rotate this triangle to fit any situation that I want. So if I'm using the x and y, I'm going to get myself a little bit confused. So what I'm going to do is I'm going to call this the hypotenuse. I'm going to call this the opposite side because it's opposite the angle. It's on the side away from the angle. And I'm going to call this the adjacent side. And if I remember my sine, my cosine, and my tangent in terms of opposite, adjacents, and hypotenuse, I can turn this thing like this. I can turn it upside down. I can put it on an inclined plane. And I don't have to keep myself straight on what is an x and what is a y, because normally I'm dealing with an x and a y in a coordinate system. That's normally how I want to think about things. So I'm going to do it in terms of this. So we get to do Pythagorean theorem, right? The hypotenuse squared is equal to the adjacent side squared plus the opposite side squared. Y squared plus x, or x squared plus y squared equals c squared, or a squared plus b squared equals c squared. Totally simple. The sine of the angle is a ratio. It's the ratio of the opposite over the hypotenuse. Cosine of the angle is the adjacent over the hypotenuse. And tangent of the angle is the sine of the angle divided by the cosine of the angle, or the opposite over the adjacent. Or you can do it in if you're more comfortable in the X and Y, so I'm more comfortable. And we're going to utilize the right triangle. Okay? So if you've had a lot of trig, this stuff's easy. If you haven't had a lot of trig, this is really the guts of what we got to work with. Okay? Really the guts of what we work with. And you've seen it over time by dealing with it in algebra, converting between these two coordinate systems. Look familiar, guys have seen it before. Also in the appendix of your book. Okay? Also in the appendix of your book, you've got, your book is really a really good resource. I really like our book. And so you really want to kind of utilize that appendix. I also will provide you extra stuff associated with it. Questions? You guys good over in Tonka while somebody speak up so that we know that you're still there? Somebody yell in Tonka.
Yeah.
Yay! Nobody's asleep. This is good. Because it is 8 o'clock in the morning. Actually, it's almost 9 o'clock now. Almost 9 o'clock. Okay, questions? Yeah, got a question? Concerns? You guys are terrified. I got a nod. At least I got somebody being honest. Everybody's been able to access WebAssign? No, too many. There are some glitches, I know. But not too many. Everybody able to find everything on Blackboard? You guys good over there? Brain's already full this morning? Okay, I'm gonna let you go.